Okay, so today we won't begin with 2i. We're going to talk about when we're going to use each different rule, okay? Because I think that's something that everyone's always struggled with. Because when you do the product rule, when you do exercise 2D, all right, all you have to do is use the product rule, okay? And then when you do the quotient rule, all you have to do is use the quotient rule. And so you don't have to differentiate when do I have to use each rule. And so now that they're starting to come to you, they're all jumbled up. It takes a lot of sort of recognition of what we need to use here. So I've thought about dividing it up like this. I think this is a good way for us to divide it up. That we have calculus techniques, okay? And that's what we use to find the derivative. And then we have calculus rules, often because we have functions that are made up of exponentials and logarithms and trigonometric functions, okay? So within the context of the product rule, you may often have to do the derivative of a trig function. Okay, so that's what that means. That's why I've split it up like this. So what we're going to do, I'm just going to flick through and I'm going to point out what is the most efficient procedure to use. Okay? Because in a lot of these, there's multiple ways of doing it, but we always want to use the quickest way, the fastest way to do it. So let's have a look at the first one here. All right, we have x to the 5 plus 4x. Take 3. So when we're confronted with something like this, we should use simple differentiation. Okay, it's pretty straightforward. Some people might look at 4x, all right, and you should know, okay, I would expect you to know, you don't need to use the product rule there to differentiate 4x. And the reason is, this is a number, okay? We only use the product rule when it's two functions. So that means that both have some variable of x in it. Here there's not a variable, so we can just use simple differentiation. All right, the same goes for when we have something like 4 sine x. All right, it's 4 times a variable, and we don't need to use the product rule because it's just a number. I think this one will pop up in our PowerPoint, but if we have something like sine x on top of 2, okay, you could use the quotient rule, right? We have one function divided by another. So you can go u and b, and you would get the right answer, but it's a really long way to do it. The best way is to recognise that this is equal to half sine x, and that's just a number, and so the derivative of half is, the derivative of sine x is cos x, and the half just hangs out. Alright, so we've got to think about these things in the simplest way we can. Okay, next example, we have x ln x. Okay, here it's definitely the product rule, because we have one function multiplied by another. They both have the variable in them. Alright, x squared on top of cos x. Definitely the quotient rule, because they both have the variable present in the quotient rule when we're dividing. Alright, we have 4x squared take 5x plus 7 to the power of 12. Definitely the chain rule, because we have a whole function to the power of n. So that's when we're going to use the chain rule, when we have a composite function. Okay, 5 on tan x. Two ways, all right? Maybe you're looking at that going quotient rule. I've got 5 on tan x. We've got u on top of v. Okay, so you can do that again, and it will generate the right solution, but it's not the most efficient process. What we should do when we have a number at the top and something at the bottom is bring the function at the bottom to the top and make the power negative. Okay? That is equal to that. And now it's just, that number's going to hang out, and it's just chain rule because it's a function to the power of n. Okay? Alright, here we have one function at the top, another function at the bottom, definitely quotient rule, but it's also going to be the quotient rule with the chain rule because we have a composite function in the denominator, we have a square root. So we've got the basic theorem is the quotient rule, and then within that we're using the chain rule. Alright, number 7, sine to the power of 3x. So just what that means is that sine of x to the power of 3, that's the way we should understand it. This is the way we write it, okay? And so then it's just a function to the power of n, we've got the chain rule. Okay. ln of x squared on e to the x. Alright, whenever we have these log ones, okay, whenever we have the derivatives of log, we should look to see if we can use log laws to simplify them. In this circumstance, we can. Okay, so those log laws, I'm not going to write them all out. ln A plus ln B. This one's ln A on B, so that's going to be ln of x squared take ln of e to the x. All right, that's what it simplifies to when we split it, and then it can simplify further. And this is just ridiculously easy to differentiate. That 2 can come out the front because it belongs to everything there. Okay, so we've got 2 ln x, and then ln e to the x just simplifies to x. And we haven't differentiated yet. Okay, so this is something I really tries to emphasize. We've got y, and then we differentiate. We do it all in one go, and we're very clear where that takes place. If you just write equals, 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 you're going to get a mark taken off. Bad notation every time you do it. All right, so make sure you use the correct notation. Okay, number 9. We have 5x squared plus 3x take 4 on top of x. Okay, so yes, you would be justified in using the quotient rule here. Alright, because you have one function divided by another, but there is a more effective way. And we did this when we did simple differentiation in 2b, that is by splitting the denominator. So what we have is we've got 5x squared on x plus 3x on x to take 4 on x. Okay, we can split it up so that the function up there is equal when it's stated like this, which simplifies to this. Okay, which is super easy to differentiate. One step, you don't need to go u, v, u dash v, alright? So no, and it's in a much simpler form as well. It's expressed in a much simpler form. Okay, now the only reason we can do that, we can split the denominator, is because the denominator is one term and it's a power of x. Okay, so we can only split the denominator if it's some x to the power of n. Here it's x to the power of 1. There's no point doing it if it's cos of x. Okay, there's no point doing it if it's a function that doesn't cancel with the powers. All right, so that's the only time we should think about it, when they're both polynomials. All right, number 10. Here we have 3 on top of 4x squared plus 7x take 5. So this is an example of when you would not split the denominator, because firstly there's multiple terms in the denominator. Alright? Multiple terms, so we can't just split them up, that's illegal. What we should do here is the chain rule. We're going to express it as 3 times 4x squared plus 7x take 5 to the power of minus 1. Okay, that's what this equals, and then differentiate from there. Okay? So, are there any questions about these ones that I've brushed over? No, so I can send this PowerPoint. But a bit later in the lesson, when we come back from recess, I've got a super awesome Kahoot with these kinds of things. And you guys, you're not differentiating it, you're just saying which rule we need to use, okay? Because I think we know how to use the rules, but that's probably something we need to practice a bit. All right, I'll press stop here. I'll get set up for our 2i.